So we're just really going to expand on the whole concept of antiderivatives. If we look at this definition, a differential equation is just an equation involving a derivative. And the order is just the highest derivative involved in the equation. Okay, so if we consider the differential dy dx that equals secant squared plus 2x plus 5, if we start with the derivative, how do we find y? We integrate both sides. The antiderivative of dy dx is y. Antiderivative of secant squared, think of your trig, tan x plus, add 1 and divide, 2x squared divided by 2 is just x squared, plus 5x plus c. So all functions is where we use the c for any constant that could be a part of the original equation. All right, so we then, we'll talk, the initial condition is when we're given an actual point that allows us to find c, and that will be the particular solution when we actually incorporate the initial condition and plug it in to find c. All right, so for example, we are given find the particular solution to this differential. So we'll do our integrate both sides. So when we integrate dy dx, we get y. Antiderivative of e to the x is e to the x minus, add 1 and divide. So it'll be x to the third. When we divide by 6 by 3, we get 2 x to the third plus c. We then can plug 1 in for x and 0 in for y. And so 1 to the third times 2 is just 2. So this one's kind of weird. When we get c by itself, I need to add 2 and subtract e. So 2 minus e, this entire thing, is c. So the particular solution, e to the x minus 2x to the third plus my constant, 2 minus e. All right, so example 3. Find the particular solution to the differential. So we integrate both sides. So add 1 and divide. Secant squared is tangent plus c. This plus c is extremely important in this first couple sections here. Y is 3 when x is 0. So 3 equals 0 squared over 2 is 0, minus tangent of 0 is also 0, which means our constant is 3. So the particular solution is y equals x squared over 2, minus tan x plus 3. All right, whether we're given dy dx or f prime of x, we just integrate both sides. When you integrate the derivative, we get f of x equals. Now, be really careful here. Okay, well, I think we're gonna actually skip this one. I got interrupted. I had to check in the hall. This is not one you're going to have to worry about for the AP test, so I want to focus on those that we will. Okay, so now let's consider the graphs. So if we consider where dy dx equals cosine, so if we think about it, when we do our antiderivative of both sides, we get y, equals sine of x plus c. So let's consider sine of x. So this would be, first of all, it's kind of bad, but we'll just extend this in both directions. So this would be the graph of when c is 0. What if the constant is 1? So then everything is getting shifted up 1. Sorry. Everything is up 1. What if it's negative 1? Everything would be shifted down 1. Probably would help if I'd so everything's kind of shifted depending on what that constant is. So this is if c is 0. If c is 1, everything's shifted up 1. If c is negative 1. So it's just all of these stacked on top of each other, and they go on forever, both directions, because we don't know what that c is. That's really what leads us into what we call slope fields. So a slope field is representing the slopes at each particular point of the derivative. Because remember, dy dx on the graph represents slope. That's hence why we call it the slope field. We're going to find each particular point and create a slope. All right, so let's consider all of the places where x equals 0. So if we plug in this whole, every single point here, our x value is 0. What is cosine? Since dy dx equals cosine, what's cosine of 0? When cosine is 0, the slope is 1. So what we do is create a little short line that has a slope of 1. Now, I think it's almost easier. I don't really like 1. What I'm going to do, let's call this pi over 2 and call this negative pi over 2. Let's label it that way because that's going to be easier for us to determine. So this whole vertical spot here is where x is pi over 2. So what does dy dx equal if x is pi over 2? What is cosine of pi over 2? So remember, cosine of 0 is 1, cosine of pi over 2 is 0, and cosine of pi would be 1. So all of the places where x is pi over 2, dy dx, or the slope, is 0, which is just your flat line. What if we go back to negative pi over 2? That's also going to be 0. So this would also have a slope of 0. every spot where x is negative pi over 2. So let's think about how this helps us. If this is showing us, let's go one further and look at all the points where x is pi. What is cosine of pi is -1. So then every spot along this spot here would be -1. So let's think about if our dy dx is cosine, what is y? The antiderivative, sine of x plus c. So what we can do is go here and follow the slopes to create our slope field. See, and this was a whole lot better graph than this one here. So here we actually have 0 slope, 1 slope, 0 slope, -1 slope. It guides our lines. So we just kind of stay within the lines. All right, so let's try this one. All right, and they also want the particular solution that goes through this point. That means we don't have a family of graphs. We have one particular solution that we will graph. All right, so this one's a little bit trickier. dy dx equals x plus y. So what we do is we have to consider every single coordinate point. Anytime there's both x and y in our derivative, it's super annoying. All right, so let's consider the 0, 0. The 0, 0 coordinate, when both x and y are 0, has a 0 slope. Now, sometimes it's helpful to look for families of points that kind of will give us similar. Like think of -1, +1. -1 plus +1 is also 0. So these two, also +1, -1. So notice there's kind of a family of graphs in this diagonal. All right, so let's consider here, -1, 0 has a -1 slope. So we have a negative slope, and usually I kind of use my points to help guide me. Consider this point. 1, 0, 1 has a +1 slope because we're taking 0 plus 1. 0, 2 has a steeper slope, but it's still positive. So typically on your slope fields, what I'm going to look for, the 0 slopes, if the positive slopes are positive and the negative slopes are negative. So consider the -1, -1, 0 has a -1 slope. This is -1, -1, that's going to be a -2 slope, so it's negative but a little steeper. This has a 1, 0, +1 slope, so I should go up. This is 1, 1, +2, 1, 2, +3. So it kind of gets hard to really distinguish the whole +1 slope, +2 slope, +3 slope. So we try and just get a little bit steeper as we go. Let's consider this point. -1, 2, that's +1, so more straight diagonal. Okay, now I don't have my graph big enough. We need to go over to 2, 0, which is a 2 slope, so a little steeper than our 1 slope. And so what's probably helpful is if we extend this just a little bit more, and this would be a +3 slope, so it's getting steeper. So what I'm going to do is I'm going to come back, and we're going to superimpose on our graph, and it's going to follow this, and it's going to get steeper this direction. Then this is just matching. So take a few minutes and think about, if you look at each of the points and consider, here we're taking x minus y, this is x times y, x divided by y, y divided by x, and match which one you think goes with which one. And then we'll discuss it more tomorrow.